Hello everyone. Today we are starting with module number 5, which is your BJT, Bipolar Junction Transistor. This is your module number 5.1. Okay, in that we'll start with BJT operation. Then we have common base, common emitter, common collector configurations, their input output characteristics. What do you mean by operating point DC biasing? And then on the second half, 5.2, we have BJT as a switch and voltage amplifier. So let's start with BJT topic. BJT stands for bipolar junction transistor. It was invented several decades back in the year 1948, so long back in Bell Labs. Alright, the types of BJT which are there are as follows. So there are two types of BJT, NPN BJT or PNP BJT. Okay, so here in NPN BJT, the majority carrier are electrons, and in PNP BJT, the majority carrier are holes. Okay, so we will require the knowledge of PN junction. So imagine we have a PN junction. Okay, so if we have a PN junction like this, which have its depletion layer already present, and we have this PN junction over here, which terminals are called as anode and cathode actually in reality. So this is bit W, width of the depletion layer, and here we have the depletion layer, which is devoid of any charges. Here we have PNN actually, we can write it over here, anode and cathode. So tell me what will happen in the forward bias. Tell me the sequence. In forward bias, if we increase the forward bias, what will happen? W will decrease, right? Yes or no? And current will increase, ID. Current ID flowing through the junction will increase. Yes or no? At least validate yes or no. So this is your symbolic form of PN junction diode. I hope I'm audible and the slides are visible. So if you apply a forward bias, the depletion region width will reduce and my current will increases exponentially. Okay, and if I apply reverse bias and I increase my reverse bias, what will happen to W? The depletion region width will become widen and widen, and my current will be non-existing. No current will flow. Of course, the current will slightly flow in practicality in microamperes. So this is called as leakage current or saturation current. So only leakage current in the form of microampere flow. That's why we say that in a PN junction only we have current in the forward direction, not in the reverse direction. It's not allowed. Alright. I think this much background you all know already, right? Hello. Can you all acknowledge? Okay. Now we are going to NPN transistor. Let's go for NPN transistor. We are drawing the structure of BJT. So it has 3 layers and 2 junctions. So you can draw along with me. It has 3 terminal device, semiconductor device. First terminal is emitter. Then we have the base terminal. This is base and this is collector. Okay. This is base and this is emitter. Alright. Now this is made up of N, P, N. In fact, the doping concentration is slightly more. So here I may write it as N plus plus, P plus, NN layer. Alright. N plus plus means that the doping is higher, maybe in the range of. So what is the meaning of this? The meaning of this is that the doping over here, ND or NA, ND is higher. Let's say in the range of 10 is to 19. per cubic centimeter. Here it is slightly less, maybe in the range of 10 raised to 18, and here it is slightly doped, maybe in the range of ND. It is number of donor ions, doping concentration, maybe in the range of 10 raised to 15 to 10 raised to 16 per cubic centimeter. Okay, that's the meaning of it. So what we can say there, that the emitter region over here, the summary will be, the emitter region is the moderate area, okay, but it is heavily doped. Emitter is heavily doped. Then we have base region. Base region area is very small, as you can see from the structure itself, and it's lightly doped. Okay, please mute your microphones, everyone. Okay, then we have the collector. Collector have the largest area, and it's also lightly doped, not much high, because see here the area is small and the concentration is 10 is to 18. Here the area is wide, but the concentration is 10 is to 16. So if you fit the same amount of area as base, then the concentration of collector is more. But in general, as per the area wise, it's lightly doped only. Okay, it's moderate. We can write lightly doped or moderately doped. It's fine. Both are fine. Depending upon how you view it. So we can say moderately. Actually, this we should write it as moderately doped, and this we should write it as lightly doped. So base is moderately doped, and collector is lightly doped. Okay, the number of charge carriers are less. Now, is there a depletion layer present over here also? Yes. This is a PN junction here also formed, so there is a depletion layer here present. Here it is. More onto the base side because of this is my depletion layer. So this is called as base emitter junction, and it's the depletion layer as well. We can call it base emitter depletion layer. Okay, is there a depletion layer between these two junctions? Yes, there are two junctions over there. So here also there are two junctions, larger on this side because it is lightly doped. Yeah, this is called as base collector junction, and this is also called as base collector depletion layer. Okay, so this is my BJT structure, NPN BJT structure. So in the exam, if they ask you about its construction, you can write it. Okay, drawn everyone. It's a three terminal device. It's a three terminal, two junctions, semiconductor device. Okay, which are the two junctions? Can you tell me? Base emitter junction, yes, and second junction is base collector junction. So the two junctions are base emitter and base collector. The emitter is having a moderate area. Base is narrow width. Base which is very narrow. Construction wise, if you want to say anything, we can say that. Base is having the smallest area, so it's having a narrow space. And collector is having the largest space. Okay. Emitter is heavily doped, base is moderately doped, collector is lightly doped. The base is having the smallest area or the narrow space, and the collector is region is very large space. Okay, everyone, completed up till now? Yes or no? Hello, can I move ahead? All right. Let me scroll up. Let me know if you're following or no. Now, Now we go to symbols of BJT. Now if you want to draw PNP transistor, it will be PNP. Same thing you will write, only the majority charge carriers here will be holes. So here the majority charge carriers are electrons. Minority charge carriers are holes here in this device, in this structure. So in this structure, majority carriers, charge carriers are electrons and minority charge carriers are holes. In PNP structure, it will be opposite. Then we'll draw the symbol. The BJT symbol will be as follows. There is an arrow in one of the terminals, that is the emitter terminal. Opposite to it, there is a collector, and this is the base terminal. So this is the diagram for NPN BJT. NPN BJT symbol. Similarly, there is PNP symbol. So PNP symbol, it is like this. For PNP, we have the arrow going inwards. Arrow going inwards. Here is the emitter terminal and here is my collector terminal. Okay. So this is the symbol for a PNP transistor. PNP. Got it? So write it down. PNP BJT. Where the majority carrier will be holes and the minority carrier will be electrons. Alright. So this is about the construction of BJT. That is NPN and PNP structure. Completed the symbol? Okay. So next we go for different regions of operation. So what are the different regions of operation for a BJT? There are total 4 different regions of operation. So what are these 4? We'll write one of them. One is forward active or active region. Now these regions are classified based on the base emitter and base collector junction. First let me write down the regions. Next is cutoff region. Next is saturation. Then we have reverse active or inverse active. Okay. Inverse active, which is not so useful. So all these can be distinguished on the basis of base emitter junction status. So this is base emitter junction and base collector junction. Based on these two junctions, we can classify into 4 regions of operation. Okay. Now whenever I write over there, okay, so giving slight trouble. FB stands for forward bias and RB, when I write it, it means reverse bias, just for your notice. So when the base emitter junction in the active region should be forward bias and base collector should be reverse bias. In the cutoff, both should be reverse bias. In saturation, both should be forward bias. And inverse active should be opposite of active region. Base emitter should be reverse bias, base collector should be forward bias. Well, the last one, the last option, we don't use it. So this is not used at all. Okay, just for your knowledge, it is there, but it is not used. When we want to use BJT as an amplifier, we use the following mode of operation. We use made of cutoff. So the application of BJT as an amplifier, we can use it in the active region. So BJT as a switch, if you want to use it as an on-off switch, so BJT in the cutoff region is fully off and BJT in the saturation region is fully on. So as a switch, we use it in the cutoff or saturation region. So these are the applications areas, or depending upon the region of operation. So if you want to make use of a BJT as an amplifier, then we operate it in the active region, or as a switch, we operate it in a cutoff and saturation region. Understood? The inverse active region is to be avoided, not used. Okay? Have you completed these different regions of operation? Yes? Okay, great. Then we go for, let's say if you want to show them in biasing actually, in the structure, these regions of operation, then we can show it as follows. So let's say we want to show active region of operation in terms of the structure. So I'll draw the structure. You can also draw it along with me. So this is NPN. You have emitter, collector, and base. Now I want to make it active region. I want to make it active region of operation. So how will I make it? So for active region, base emitter junction should be forward bias. So how do we forward bias it? Negative to E, right? And positive to B. Yes or no? This is forward bias, right? Hello. This is forward bias and this should be reverse bias, base collector. So this we can call it as VBE, is forward bias. Then base collector should be reverse bias. That means P should be connected to minus, like this. This is reverse bias. This is VBC. Okay. So this is how we bias NPN BJT in active region. Now if you want to bias a PNP BJT in active region, how it will be? Let's draw a PNP BJT. So tell me, how will I bias it? This is collector, emitter, base. So base emitter should be forward bias like this. And your base collector should be reverse bias, so here it will be positive. VBC, VBE. Alright? Understood this? So this is how we bias the BJT. This should be forward bias and this should be reverse bias. Let's do it for cutoff and saturation also. So for BJT to be in the cutoff region, what should be the biasing? Both should be reverse bias, right? N, P, N. So this is emitter, base, collector. So reverse bias means what? N should be connected to P, positive side of the battery. Here P should be connected to negative side of the battery. So here it is. Now both are reverse bias. Correct? So this mode of operation is cutoff. This is cutoff region. And finally saturation region. So draw the NPN structure. N, P, N. This is emitter, base, collector. So here in saturation both should be forward bias. So this will be forward bias as follows. And this will be also forward bias as follows. Okay. So this is saturation mode of operation. Saturation region. Alright. Completed drawing. Hello. These are the different operating, according to the operating region, the structural external bias connected to them, such that they are in active, cutoff, and saturation region. Have you completed this, students? Yes, no? Can I move on to the next one now? Okay. All right. Next we go for the technical definition now. The principle of operation of BJT and the technical definition. So write down what do you mean by bipolar. So bipolar means the charge carriers are of both polarities. The charge carriers are basically electrons and holes. Charge carriers are of both polarities present over here. That means electrons and holes. Both are of both polarities. Both take part, both participate in current conduction process. So electrons and holes both take part in current conduction process. That is what is the meaning of bipolar. Then we write the principle of BJT, bipolar junction transistor. Let us write the statement. So it involves, write down, it involves the use of the voltage between two terminals. The voltage between two terminals here will be VB, base and emitter terminal. So it involves the use of the voltage between two terminals to control the current flowing in the third terminal. So current flowing in the third terminal is IC, that is collector current. Okay, so it involves the use of voltage between two terminals to control the current flow or current flowing in the third terminal. All right, written. Next we go for BJT configurations. Now BJT operating regions is different, BJT configurations are different. So we'll write down BJT configurations. All right, so there are three configurations of BJT: common emitter, or it's also called as CE configuration, then common base configuration, which is called as CB configuration. Then we have common collector configuration, CC configuration. Okay, so basic operation will can be determined as follows. So in case of common emitter, here it is. In case of common emitter, this is base, collector, emitter. The emitter terminal is common between the input and the output. So this is the input, this is the output. So emitter terminal is common between the two. That's why it's called as a common emitter. Then we have common base, which I am showing over here. So this is the input. Let me write the input like this. This is the input, output, and the common terminal is base. So common base configuration. So this is emitter, this is collector. Then the last configuration will be common collector. So here we have connected the transistor as follows. So here input is between base and collector, and output is between collector and emitter. This is collector, base, emitter. So here the collector terminal is common between the input and output. That's why the three configuration names are common emitter, common base, common collector. Okay, and we will be studying now mostly the working of the BJT in common emitter configuration mode, which is next, coming up next in few seconds. Okay, are you following till now? Till now I have not explained the working of the BJT. Now I am explaining the working of the BJT. Can I start? It's all there. I mean, if you miss out on writing something, it's all there with you all. No, don't worry about it. Only concentrate on you don't miss out on the learning part, the concept part. So BJT principle I'll be repeating again and again. No worries in that. It involves the use of voltage between the two terminals to control the current in the third terminal. That is true. So now can we start now? Hello? The working? Okay. Before I start, let me rewind you for a PN junction. In a PN junction, if you are in the reverse bias, if you are under reverse bias and you go on increasing the reverse bias voltage, that is VR, you go on increasing, what will happen? The width will increase, right? W will increase. What else will happen? The electric field, which is from positive to negative or negative to positive? Positive to negative. So the electric field will become very much powerful. So electric field is very powerful in reverse bias. That's what I wanted to point out. By the way, electric field will be given by voltage upon length. Its unit is volt per centimeter. Okay. So here, of course, the current is very small. So this I have to point out that depletion region will go on increasing because we are removing the carriers from the junction. And the electric field is very powerful. Okay, so this is a revision of concept which I want to bring you to attention. All right, can we start with the working now, everyone? So pay attention now. So I'll be explaining the working of NPN BJT in active region. Common emitter configuration. All right. So for simplicity, I will be explaining. What do you mean by active region, by the way? Can someone tell me? Active region means what? Base emitter junction should be forward bias and base collector junction should be reverse bias. Okay. And in the base collector junction, the electric field is very powerful. The electric field is very powerful. That is what we need to remember. Okay. Yeah. So I will be drawing the first of all the emitter and base region. So this I'm drawing it vertically now, like this. So this is base. This is my base region, and this is my emitter. All right. So what is the condition for it to be connected in? It has to be connected in the forward bias mode. So this is made up of N plus plus. This is P plus. So I'm connecting positive over here, negative over here. So it will make it forward bias. Yes or no? So I'm applying VBE, which will make the junction, base emitter junction, forward bias. Agree? Hello? I require your consent on this. Please say yes or no. Hello. So right now, just concentrate on I'm applying. This is P. This is N region. This is P region. So it's a PN junction. Yes or no? Hello. Can I get a confirmation from you all? Okay. So it's a PN junction. There will be a depletion layer which will be very, very, in the forward bias, it's very, very less. So if you draw it, if you don't draw it, it's fine. So what happens when we increase the forward bias voltage? What plan of action takes place? Can you tell me sequence of operation? Number one, you you apply VBE such that it makes base emitter junction forward bias, and you now increase the value of VBE. What will happen? Can you tell me? What will happen? Come on. Hello, come on. What will happen? There are electrons over here, plenty of them. The carrier concentration is doping level is high, and there are holes over here. What will happen? Tell me. No, it's a forward bias. We can say the most of the electrons will diffuse across the junction, will go to the n side, because these electrons cannot be attracted towards the negative side of the battery, so their only option is to go above. So these electrons mostly they'll flow in this direction, whereas see the concentration is very, very high. Let's say for example there are around 1 lakh electrons are there, okay, and there are around 1000 holes are there. So out of 1 lakh, few of them will go into the bay. I mean, all or mostly, if we keep on applying VB higher, the IE emitter current will go on increasing exponentially. Yes or no? That is what we have studied, right? The current will go in from bottom to top. Uh, Electrons will go from bottom to top. So current will go from top to bottom. So this is the IE current. So out of 1 lakh electrons, most of them will cross the base junction. Okay, so some of them will recombine with the holes present over here. There are 1000 holes. So some of them will be recombining with them, giving it to new electron hole pair. So there will be some what formation of a small hole current will also flow over here, because the concentration in base is less. Base, first of all, region is also less area wise. This is area wise, let's say 10 times bigger than the base. Okay, so by the time the electrons reaches over here, some of them recombine and more electrons come over there. Okay, so this is clear to you. So if we have plot the characteristics of VBE versus this is VBE versus the base current. If I compare the base current versus VBE, the graph will be exponential in nature, like this, following the nature of PN junction diode. Well, because here the input current is IB. IB is the input current. And what is controlling IB? Input voltage. What is that input voltage? VB. So VB controls IB. Controls IB. Okay, so that's why we say na voltage at the two terminal control the voltage at the third terminal. That is what we have said. But this in turn will control IC. That is what we will see now. VB will control IB. That itself will control IC. We'll see now how. Now, this much is clear to you. This is what will happen. Most of the electrons will go from the emitter region to the base region. Some of them will recombine with the holes over there. Okay, but now what we do is we have one more region which is very, very large. Okay, which is my N region. It is also made up of electrons, but these electrons are not so quite high. Now I am connecting it to another supply. Now base emitter base collector junction should be what? This is collector junction. should be reverse bias, right? So reverse bias, you show it how? Let me show it on the other side. Here it is. Okay, so this makes the base collector junction reverse bias. VCE, I'll correct it. VCE. Alright, now what will happen? Basically, if we want to connect, first of all, base collector junction, so it's suitable to show it over here first. So let me connect this writing pad again. So let me show you base collector junction only, externally biased. Here it is, the supply voltage coming up, and this will be connected how? Positive here, negative here. Okay, reverse bias it should be, right? This is VBC. Now what will happen? Can you tell me? Will there be a depletion layer formed over here? Yes. This will be lesser on this side, more on this side. So there will be this depletion layer present. This is base collector depletion layer. That depletion layer will go on increasing. That's fine. But what else will happen? Tell me. Will these electron, will this, where will these electrons go when they have come over here in the base? Can they return back to emitter, or will they move forward to the collector region? Hello, are you listening? Now over here the situation arrives that the electrons are traveling to the base region. Most of them. Let's say out of 1,90,000 of them are traveling to the base region. Some of them are recombining. Where the others will go? All the other electrons will go to the emitter region. Why? Because emitter is saying positive supply. It's very, very powerful. And emitter electric field is also very, very powerful. Here it is. The electric field of the base collector junction. It's very, very powerful. So as soon as you see any electrons over here, it will pull it. So collector region is like a pull region. It's pulling the electrons which are coming from the base. And this emitter junction is like pushing. So your push-pull arrangement is happening. So the supply voltage VB is pushing more and more electrons into the base region. And collector region is doing what? It's pulling the electrons from the base to the into the collector region. So collector region already has electrons, but they are very few in number, lightly doped. Okay, so these electrons are maybe in the range of 10,000 or so. So, but 90,000 are coming its way. So what is more dominant? 90,000, right? So that's why these electrons will join them. Maybe from 90,000, some 85,000 will join them, and that will constitute to the collector current, like this. Remember, the collector current will be slightly lesser than the emitter current. The emitter current is the highest, okay, because that is the source of electrons. So that is where the electrons are getting emitted from in the first place. Collector junction is called as the collector because all the electrons, the majority carrier electrons are getting collected at the collector terminal. They are moving out of the terminal from the collector. So this is my collector current. Let me mark in blue. Collector current. Okay. So these are my terminal currents. So there are my output current. My output current is IC. Okay. So VB controls IB. Okay. And in turn it controls IC. Now I'll explain you everything in bits and pieces. So now let's consider. I have applied VB. VB is increased. I increases exponentially. Okay. Some of the electrons gets recombined with the holes over here, and some of this constitute to base current. So base current is quite small. Okay. So even if I have written over here IE, it doesn't change anything. IE, it's still exponential in nature. Okay, so when I plot IB versus VB, it's a input graph, input characteristics graph. All right. And now let's say 95% of the electrons from the emitter after reaching the crossing the base junction reaches the collector junction. Now why they will go to the collector? Because of very powerful electric field. They will be attracted towards this positive side of the supply, because reverse bias is very high, forward bias is very less, maybe in the range of 1 volt. This is in the range of 10 volt. So electric field is 10 times more powerful. Okay, so all of these electrons are pulled into the collector region, and where they constitute the collector current. All right, yeah, understood the working. Why the base should be thin? Because the thinner the base, the more the lesser recombinations will happen, the more current can flow through the more of the electrons can go into the collector region. So that's why it is the base region is kept very small, so the number of recombinations are less, electron hole recombination. All right, so if I want to join, if I want to write all the currents, the terminal currents, what will be the terminal currents given by? Which are the terminals? Base, collector, emitter, right? So terminal currents will be IE, IB and IC. Do they three have a relationship between them? Yes. IE is the total current, is the combination of IB plus IC. See, a small amount of base current will flow because of these holes. There are holes in the N region also. Okay, that will contribute to the base current, and some of the holes will recombine. So that will also contribute to the base current. Okay, then most of these electrons will reach over here. All right, but some of the holes are also present in the N region. Okay, so they will contribute to the leakages which are present. So some of the leakage currents are also present, which will contribute to very low current. But majority we have IC plus IB is equal to IE. That is the relationship between the three currents, terminal currents. What are the terminal voltages? VBE and VBC. All right. Okay. So this is how the operation of, the working of NPN BJT operates in the active region of operation. All right. So initially VB is small. When we increase it, your most of the electrons will cross the base junction and reach the collector, and that's how it constitutes the current, collector current, base current and emitter current. Have you understood the working of NP and VJT in active region now? Hello? Yes, no? Little bit? The more will be clear to you when we study the characteristics of it. Right now I can only tell you this much information. By the way, what is the base width now? The base width has reduced as we go on increasing this. So this is the active base width now. Of course, there will be a depletion region here also. So this is WB, width of base. So as you go on increasing the reverse bias, this width of base goes on reducing. So remember that. Okay. Now, now the relationship between the currents. Let's write it down. So it can be shown that this IE will be in milliamperes, IB will be in microamperes, and IC will be in milliamperes. Maybe in numbers, 1 milliampere, this will be 1 microampere, maybe 0.99 milliampere, maybe. So this is equal to, emitter current is IB plus IC. Also, there is a relationship between, this will be seeing in the other characteristics, but we'll write it down. IC is equal to beta times IB, where beta is the current gain, IC upon IB. It's output current, IC is the output current, and this is the input current. And beta is called as the current gain of BJT. We have one more current gain, the emitter current is almost similar to, practically almost similar to IC, because very small amount of base current flows, but practically we can write IC is alpha times IE, where alpha is also the current gain but less than 1. This beta is greater than 1. So alpha is given by IC upon IE. This is also current gain, but this current gain is less than 1. Okay, so we can rewrite this equation as follows. IE is equal to, instead of IB, what do we write? Instead of IC, what do we write? Beta IB plus IB. So we can take beta common, IB common, and we'll get IE in terms of IB. Okay, so IE is 1 plus beta times IB. Okay, this way we can do it, or else we can also write it as follows. We can also derive it other way around. These are a definition of current, currents. So I can rewrite this equation as follows. IE is IC plus IB. IC can be written as alpha. IC can be written as, sorry for this, alpha IE. This is IE plus IB. Let me add it over here. This is IB. This can be written as follows. 1 minus alpha into IE is equal to IB. Okay. And IE in terms of IC can be written as, what is the relationship? IE will be IC upon alpha, right? So this will be IC upon alpha. So this can be written as IC is alpha upon 1 minus alpha times IB. Okay, and this is actually called as beta. So now beta is nothing but alpha upon 1 minus alpha. Alright, which is the current gain, and that I've already told you the relationship between IC and IB. Beta is the current gain. Its value is from 50 to around 400. Okay, this is the current gain. Alright, that's why BJT is called as a current control device. Have you completed writing this, everyone? Yes, no, what? Please complete it fast. Alright. So why BJT is called as a current control device? Because in simple language, VBE is controlling IB and IB in turn is controlling IC. Alright, because we have seen the relationship between them, right? If I control IB, I can control IC because IC is just beta times IB. Okay? Now we go for different configurations of BJT. Different characteristics, we can say input output characteristics. So we'll draw them today and then we'll explain them next time. So can we start? We'll just draw the characteristics and keep. I'm not explaining them. I'm telling you. I'll explain it in tomorrow's class. Tomorrow again we'll keep it normally in the afternoon only around 2 p.m. or 3 p.m. I'll inform you all in advance. So now let's discuss about the BJT characteristics, the input output. Let me go to the first page. So we'll go to, we have completed BJT construction and operation. Now we are going to input output characteristics of CB, CEC and CE. Okay, I'm just drawing it today. Then later on, tomorrow we'll explain them one by one. So let's start with, so please write down along with me. Let me connect this writing pad first. Yeah, it's connected now. So let's write down BJT characteristics. So please write along with me. BJT characteristics. There are two types of characteristics. Input characteristics and output characteristics. Okay. Now input characteristics mostly will be between, it will be between input current versus input voltage at a constant output voltage. Okay. Output characteristics will be between output current versus output voltage at constant input current. All right. And we have how many configurations we have? So the configurations of the transistor, that is BJT, are based upon the connection of the transistor terminal. So there are three configurations. Which are the three? Can you tell me? Common emitter, common base, common collector. So each of them will have input characteristics, output characteristics. Input characteristics, output, input characteristics, output characteristics. All right. So the operation of the BJT is slightly, which we have discussed today, it's incomplete. When I discuss the common emitter input output characteristics, that time when I complete the explanation, that explanation will be complete then with the working. So you can add the working wala details there itself. Because after explaining the working of NPN BJT in active region, we have to draw input and output characteristics for this device. All right. So can we start with common emitter configuration? We will be plotting only the characteristics today without justifying much and telling what all things we can verify it from there. Can I start? Hello? Okay. Now I will teach you a practical circuit also and a conceptual circuit also. So let's start with the first one. First let me explain everything and then I'll draw the circuit diagram. Let me go for a conceptual one. Common emitter configuration. So write down common emitter configuration. So in common emitter configuration, conceptually, if I draw, this is what I have. Okay, here I have to draw it over here. Yeah, this is situation is what I have. This is my collector, emitter, and base. This is my input. This is my output. All right. Now, tell me which is my input current. It's IB. Output current, IC. Input voltage, VB. Output voltage, VC. Got it? So what are my input parameters? Input side circuit, input current is IB, input voltage is VB, and at the output side, tell me, it's IC and VC. Got it? So when I want to plot the input characteristics, now I am plotting the input characteristics. Input characteristics. So it's a graph of input current. So in what is the input current? Come on, tell me. IB versus input voltage VB at a constant output voltage. So what is the constant output voltage at constant VC? Got it? So it's a graph of current will always come in the y-axis. So IB versus VB at a constant VC. So this graph will be like this. It will be exponential in nature. And if I increase the value of VCE constant more to a higher value, I'll get a graph like this. So this is for VCE value 2, this is for VCE value 1, where VCE2 is greater than VCE1. Let's say this is 10 volt, this is for 5 volt, constant value. So this is the graph of input characteristics. Understood this? Have you drawn the graph? Yes? Now from this graph, what information do you get? So what information do you get? I'm writing in brown color. We can take here, see, it's an exponential curve. A segment of this exponential will be a constant. Yes or no? So I can take slope of this exponential, that is almost delta IB versus delta VB, and 1 upon slope will give me input resistance Rn, which will be delta VBE upon delta IB at VCE constant. So this will give me the information about the input resistance or input impedance of BJT in common emitter mode. So if I plot this graph and I take the slope of this curve, and 1 upon slope will give me the resistance. Slope will be y2 minus y1 upon x2 minus x1, right? So this is 1 upon slope. That will give me the input resistance. So input characteristics graph will give me the information about input resistance or input impedance of the BJT. Okay, got it? Can I move on to the next one now? Now we'll talk about the output characteristics. So output characteristics is a graph of output current, which is IC, versus output voltage, which is VC, at a constant input current value, at constant IB. Alright, so can we start with the graph? So output graph looks like this. So we have IC versus VCE. The output graph will be like this. One at one constant value of IB. So this IB is constant. Alright. So what information do you get from the output graph? If I take this slope, this value is how much? Delta VC. This value is how much? Delta IC. So this graph will give me information about R out, which is delta VCE upon delta IC at constant IB. Okay, so R out is nothing but my output impedance of BJT. Input output impedance, I'll talk about it in the next class, but just write it down what the graph information will be providing. Okay. The output characteristics can be a family of curves also. So you can plot with different values of IB. This is VC versus IC graph. Let's plot different values of IB. So let's say one value is over here, other over here, other over here. So this is IB1, IB2 constant, IB3 constant. So you can see three values of base current constants are there, where IB3 is greater than IB2, greater than IB1. Alright, this is a family of curves. And this graph, if I measure it over here, correspondingly this will be IC2, correspondingly this will be IC1. So IB2 minus IB1 divided by, I mean IC1 minus IC2 minus IC1 divided by IB2 minus IB1 will give me beta AC. So beta AC will be delta IC upon delta IB. So this is delta IB, this is delta IC. So it will give me information about the current gain. Now this is called as common emitter current gain. Common emitter current gain, because it is in the common emitter configuration. So it is called as common emitter current gain, and this is measured at constant what? If you want to measure beta, it is measured at a constant VC. Okay, at same value. Here it is, let's say. So at a constant value of VC, if you want to measure. Got it? So output characteristics of NP and BJT can give me information about output impedance of the BJT and its current gain value. Also, it will give you one more information about its operating regions. So I can show the operating regions here itself. Pardon me for doing it over here again. Let me draw it one more time. So x-axis will be VCE, y-axis will be IC. This is the family of curves which we have. Different values of IB. So this is IB1, IB2, and then we have IB3. So we have different regions of operation here. So 1, 2, 3. So if I am in this region of operation, I am in the saturation mode. This is saturation region. This I'll explain tomorrow, but right now I'm giving you just information. This is active region. And there will be one graph which will be almost parallel to the x-axis, where we can say it's cutoff region, where there is slight amount of current present, which is the leakage current U2. So this is called as cutoff region. So the output characteristics also give me information about which region of operation my BJT is operating. So whether BJT is operating in the saturation region, active region, or cutoff region. Okay, so it will give you three pieces of information. It gives you information about output resistance of BJT or output impedance of BJT. It gives me information about how to calculate common emitter current gain, and also about the operating regions of the BJT. Okay, don't worry about how we got this graph. We are going to explain that tomorrow. Don't worry about it. Okay, right now you just note it down. Completed this, everyone? Just 5 more minutes. Completed his drawings, input and output characteristics. Now we go for next configuration, which is common base configuration. Acha, before going to common base configuration, the practical circuit, this is not a practical circuit, right? For the common emitter configuration. So practical circuit is made like this. Okay, you have been connected a resistor over there to protect the BJT from heavy current, Then you apply forward bias voltage like this. Here you apply voltage like this. This is VCE, VB, this is RB, this is RC. So this is the practical circuit for implementation of common emitter mode. This is a VBE, this will be VCE, this current will be current IB, and this will be current IC. So this circuit you have to draw in exam, not this one. This one just for your understanding purpose. So this is the circuitry. If you do the experimentation with this circuitry, you will get this. Remember, you have done one of the virtual labs, so it was this circuit which you have done on. RB value is normally very high, maybe around 100K, and RC value is around 1K. So that's the range. Okay. Now you vary VB and VC, and then everything else will continue. Sorry. You have any doubts? Someone has kept the microphone on. Okay, now we go for common base configuration. So conceptually common base configuration, let's do it first. And then at the end, I'll show you the actual graph. So this is emitter, this collector, base, common base configuration, right? This is my input. That's my output. And here I have output current in the form of IE, correct? So here will be IE. Voltage will be, input voltage will be VB, right? So here it will be VB. Okay. Then we have output. Output may we have VBC or VCB. Okay, and there will be output current. So here at the input side, what do we have? Let us write it down. Okay. Input side we have input current IE, input voltage VBE, and at the output side we have output current IC and output voltage VCB. Alright, so let's see the graph, how the graphs will look like. First we'll go for input characteristics. So input characteristics is a graph of input current versus input voltage. So it will be a graph of IE versus VB. Alright. So when you plot at a constant value of VCB. Okay. So you will get a graph which looks like this. So this is VBE versus IE. This we have discussed before, right? It will be an exponential curve again. For one constant value of VCB. For another constant value, it will be slightly this way. And this value will be VCB1. This value will be VCB2. And basically VCB2 is greater than VCB1. So this is around 10 volt. This is around 5 volt at a constant value. Alright. So again, this graph will give me information about the input resistance of the BJT in common base configuration. So if I take this point and this point, it's almost like a straight line. So this will be delta VBE divided by delta IE. So Rn will be delta VBE upon delta IE. That is the input resistance of the BJT in at what constant? At constant VCB. So this is input impedance of BJT. Input impedance of BJT in common base mode. Alright. So this is what input characteristics will look like. Okay, can we move on to the output characteristics? We'll explain all these characteristics tomorrow, don't worry. Can we move on now to the next one? Next is the output characteristics. Please plot it. So output characteristics is a graph of output current IC versus output voltage VCB at a constant input current value at a constant I value. Alright. So here, if I plot this characteristics, let me plot the family of curves together. It's a graph of IC versus VCB, and it goes to negative also. So here, starts from here, up till here is almost constant. Almost constant it is. Let me keep some distance. Okay, almost constant. And here it will go to the negative side, like this. Okay, so this is the graph. Alright, it will meet at a negative axis. Let's say this is -1. So again there will be a slope, slight slope in increase, but this won't be exactly a straight line. There will be slight slope like this, slight increase in the current. This is for different values of IE. So IE3, IE2, IE1. Alright, here I can show the different regions of operation. So from here to here, this region is saturation. Then I have cutoff region like this from here to here. This is active, sorry. And there will be a cutoff region almost on the x-axis because the value of the current is very low, somewhere around here. So this is my cutoff region. Okay, so again it shows you the different operations, region of operation of a BJT, the output characteristics. Well, I can also determine the value of R out. How will I determine the value of R out? I'll take two values, one from here and one from here. That will give me delta VCB, and this value will give me delta IC. Okay, so R out I can measure. It's delta VCB upon delta IC at a constant IE will give me the output resistance or output impedance of BJT. Output impedance of BJT. I can also calculate alpha. So what is alpha? Actually alpha is IE upon IC, and IE upon IC is almost constant over here. Alright, so I can calculate alpha AC, which is delta IE upon delta IC from the same graph. Now how to find that is as follows. At a constant VCB value. So at a constant VCB value, calculate how much is IE, how much is IE2 and IE3, and then extrapolate on the left hand side and calculate how much is IC and IC value correspondingly. So this is measured at constant VCB value. Okay, so that's all about the output characteristics of common base configuration. You can measure, determine the different regions of operation, that is cutoff, saturation, active region of operation, and the cutoff region. You can find. All right. So can we go to the last one now? Acha, what is alpha called as? Alpha is also called as a current gain, but this is called as common base current gain. Beta was called as common emitter current gain. Then this current gain value is less than 1 always. Its value is very small, less than 1. Okay. Can we go to the next characteristics, the next configuration of the last one, common collector? Hello, yes. And then we'll stop for today, and tomorrow we'll resume with the common emitter mode working. So let's write the third one. Acha, before that, what is the actual circuit over here for this? This is a conceptual circuit. Actual circuit will consist of resistors. Okay, so it will consist of two resistors, one over here, one over here. This will be RE, RC, and here I have to forward bias it. So this is NP. So this will be like this, VBE. Okay, and here I have to apply, this is P, so I have to apply reverse bias at the base collector junction. So this will be VCB. I mean, I'll apply the supply voltage, I'll name it differently. I'll name it as VBB and VCC, and these voltages I call it as plus minus VBE, and here it will be plus minus VCB. Okay, the current over here will be IE, and the current over here will be IC. This is a practical circuit which will give you this characteristics. Understanding? Hello? Are you following? So please note down this. This is RC and the current flowing is IC. So by varying the value of VBB and VCC, you will get the input and output characteristics as follows. Now common collector, it has its applications. We'll now go to common collector configuration. In common collector configuration, let me draw it. So we have emitter terminal over here, collector terminal over here, base terminal over here. So this is my input, this is my output. Output is, as you can see, input current will be IB, input voltage will be VBE, input voltage will be VCB, sorry, not VBE. We can write it as VCB. Let me open this PDF again. I have saved it. It's taking some time to open it, so let me open it again. Because a lot of information has been written in this PDF, right? So it's taking its own time in writing. So here the output current will be, input characteristics will be IB versus, so input side, we have input current is IB, input current is VCB. What about the output side? Output voltage is VCE, output current is IE. Okay, this is the output current, and this is VCE, this is VCB. Okay, so here we have input characteristics as follows. This graph is slightly strange. I'll explain it to you why in next class. So it's a graph of input current, which is IB, versus output versus input voltage, which is VCB, at constant output voltage, which is VCE. So let's draw that graph. This is IB versus VCB, and the graph looks slightly strange like this. So for different values of VCE, where VCE2 is greater than VCE1. Alright. So from this graph, I can determine the value of Rn. Okay, basically over here. So this is delta IB and this is delta VC. So Rn input resistance will be delta VCB upon delta IB at constant VC. Okay. So in common collector configuration, Rn value is pretty high, and that's it uses it for its advantage. So this value is pretty high. So it has its own applications. Rn is called as the input resistance of the BJT in common collector mode. Are you following? I mean, I'm not explaining the characteristics right now. I'm just noting it down so that you all can also note down. I'll be explaining it tomorrow, each of them in detail. Right now, just you keep it in your mind. Okay? So it will have its own application. Input impedance means very, very high for common collector configuration. Alright? Can I go to the output characteristics now? Last one for the day. Output characteristics. It's a graph of output current IE versus output voltage VCE at a constant input current at IB constant. So this is similar graph to the output characteristics of common emitter configuration. So we have VCE versus instead of IC we have written IE. So the graph will be exactly similar to what we have discussed before. This one. Yeah, this is how the graph looks like for different values of IB. So this is IB4, IB3, IB2, IB1, all the constant values. So from here also we can determine the cutoff, saturation and the here this is saturation region. This will be active region and the final this one will be cutoff region. Here you can determine R out also. So R out will be delta VCE. So you can take the slope of this curve, it will be delta VCE like this. Delta VC upon delta IE. So R out at IB constant. So one of the features of common collector configuration is that it has very low value of output impedance. So this R out value is low. Okay. R in value is high. So input impedance of a common collector, uh, in a common collector mode and output impedance is high and low respectively. So this is all we will be explaining you all tomorrow by tomorrow. So for today, that's it. Tomorrow I'll explain this characteristics in detail with the help of the structure and working. Alright. So that's all for today.